In February 2026, Elon Musk announced that SpaceX was shifting its focus from Mars to the Moon. After 2 decades of promising a city on the red planet, the company admitted that a lunar settlement could be built in under 10 years, while Mars would take more than 20. Nobody seemed to notice what this actually meant. The most prolific rocket company on Earth just told the world that building a city on Mars is not a rocketry problem. It is something else entirely. Something far harder. Something that no launch vehicle, no matter how powerful or reusable, can solve alone. This is the story of why SpaceX may take humans to Mars, but will almost certainly never build a true city there. If you want to understand what separates a bold rocket from a living civilization, hit that like button and subscribe. Now, settle in and get yourself comfortable. Let's begin. The story begins with a man standing on a stage in Guadalajara, Mexico, in September 2016, describing something that sounded like science fiction delivered with the confidence of an engineering presentation. Elon Musk stood before the International Astronautical Congress and unveiled what he called the Interplanetary Transport System. The rocket on the screen behind him was enormous, taller than the Saturn V that carried Apollo astronauts to the moon, more powerful than anything ever built, and unlike every rocket in history, it was designed to be fully reusable. The stated goal was not simply to visit Mars, it was to build a city there, a self-sustaining civilization on another planet, 1 million people living and working on the red planet within our lifetimes. The audience applauded, the internet erupted, and a dream that had lived in the margins of aerospace engineering for decades suddenly had a company, a rocket, and a timeline behind it. That presentation was not the beginning. Musk had been talking about Mars since the earliest days of SpaceX. As early as 2007, he publicly stated a personal goal of enabling human settlement on Mars. But the roots go even deeper. When Musk founded SpaceX in 2002, he had just returned from a series of trips to Russia, where he had tried to purchase refurbished intercontinental ballistic missiles to use as launch vehicles for a Mars greenhouse experiment. Over multiple visits, the Russians kept raising the price and eventually made clear they did not take him seriously. On the flight home, Musk ran the numbers and concluded he could build his own rockets for a fraction of the cost. SpaceX was born not from a desire to launch satellites, but from a desire to make Mars accessible. The company would later name its interplanetary vehicle concept the Mars Colonial Transporter, making the founding ambition explicit in the hardware itself. SpaceX was not established to service the International Space Station or deploy Starlink internet satellites. Those were revenue-generating stepping stones on a path whose ultimate destination was always the 4th planet from the Sun. Every Falcon 1 failure in the mid-2000s, every Falcon 9 flight, every Dragon capsule docking, every Crew Dragon mission carrying NASA astronauts was a demonstration of capability and a generation of revenue that funded the next step toward Mars. This long-term vision attracted believers not because it was easy to achieve, but because the man proposing it had a track record of doing things the establishment called impossible. To understand why the Mars City vision gained such extraordinary traction, you need to understand what SpaceX had already accomplished by 2016. The company had done something the entire aerospace industry considered fundamentally impossible. It had landed an orbital-class rocket booster back on Earth after delivering a payload to space. The first successful Falcon 9 landing happened in December 2015, less than a year before the Guadalajara presentation. That single achievement represented a revolution in spaceflight economics that is difficult to overstate. Every rocket before Falcon 9 was disposable. You built it, you fueled it, you launched it, and the booster fell into the ocean or burned up in the atmosphere. The cost of reaching orbit remained staggeringly high because you were throwing away the most expensive part of the vehicle every single time. It was as if every airline flight required building a new aircraft from scratch before each departure. SpaceX changed that equation. A reusable booster could fly again and again, dropping the cost per kilogram to orbit by an order of magnitude. By 2025, individual Falcon 9 boosters had flown more than 20 times each. The turnaround time between flights had shrunk from months to weeks. The company was launching more mass to orbit than every other launch provider on Earth combined, including entire national space programs. This was not hype. This was not a PowerPoint presentation. This was demonstrated, repeated, measurable engineering success verified by paying customers who trusted their multi-hundred-million-dollar satellites to SpaceX vehicles. Starship emerged from this momentum, originally called the Mars Colonial Transporter, then renamed the Interplanetary Transport System, and later informally called the Big Falcon rocket. The vehicle went through multiple design iterations over the better part of a decade before settling into its current form, a fully reusable two-stage system consisting of the Super Heavy booster and the Starship upper stage. The numbers are staggering, even by spaceflight standards. The full stack stands approximately 120 meters tall, roughly the height of a 40-story building. The Super Heavy booster generates approximately 74 meganewtons of thrust at liftoff from 33 Raptor engines, burning liquid methane and liquid oxygen. This makes it the most powerful rocket ever to fly, surpassing the Saturn V by a significant margin. The Starship upper stage, which also serves as the in-space transport and landing vehicle, is designed to carry over 100 metric tons to low Earth orbit in its reusable configuration and even more in expendable mode. The choice of methane as propellant was deliberate and tied directly to the Mars vision from the earliest design phases. Methane can theoretically be manufactured on Mars using the Sabatier reaction, a well-understood chemical process that combines carbon dioxide from the Martian atmosphere with hydrogen extracted from subsurface water ice to produce methane and water. This means Starship would not need to carry return fuel from Earth. It could be refueled on Mars using local resources. This single design decision transformed the architecture from an expendable one-way delivery system into a potentially reusable interplanetary shuttle that could make the round trip. On paper, it was elegant. It was also completely unprecedented. No one has ever manufactured rocket propellant on another planet. The MOXIE experiment on Perseverance demonstrated oxygen production from Martian carbon dioxide at tiny scales, producing roughly 6 grams of oxygen per hour. But the gap between a tabletop demonstration and industrial-scale propellant production sufficient to refuel a Starship, which requires approximately 1,200 metric tons of propellant, is enormous. The Sabatier reaction itself is well proven in chemistry laboratories, scaling it to produce hundreds of tons of methane on Mars, using locally mined water ice and atmospheric carbon dioxide in a dusty, freezing, low-pressure environment, with equipment that must function reliably for years without Earth-based maintenance support, is an engineering challenge of the first order that has never been attempted. By 2025, SpaceX had conducted more than 10 integrated flight tests of the full Starship stack. The testing program embodied the philosophy that had made SpaceX successful across its entire history. Fly early, fly often, fail fast, learn from every failure, and iterate relentlessly. Early tests ended in spectacular failures that were broadcast live to millions of viewers around the world. The first integrated flight test in April 2023 saw the vehicle tumble out of control after multiple Raptor engine failures and the failure of the stage separation system. SpaceX triggered the flight termination system, destroying the vehicle approximately 4 minutes after launch. The launch pad itself suffered extensive damage from the exhaust of 33 engines, firing simultaneously without adequate flame deflection infrastructure. Critics declared Starship a failure. SpaceX saw it as data. The second integrated test in November 2023 achieved stage separation but lost the upper stage during a propellant venting event that triggered the automated termination system. The third test in March 2024 flew much further, reaching space and completing most test objectives before the upper stage broke apart during re-entry. Each flight pushed the envelope further. The fourth test in June 2024 achieved a controlled splashdown of the upper stage in the Indian Ocean, the first time Starship had survived the entire flight profile from launch through re-entry. The fifth test in October 2024 produced the chopstick catch that captivated the world. Subsequent tests through 2025 continued refining re-entry procedures, thermal protection systems, and booster recovery, though not without setbacks. A flight in January 2025 successfully caught the returning booster, but lost the upper stage when a propellant leak triggered a fire and the flight termination system destroyed the vehicle over the Turks and Caicos Islands. A March 2025 test successfully caught the booster, but lost the upper stage during its ascent burn, when 4 of 6 engines shut down prematurely. A May 2025 flight saw the vehicle spin out of control due to a fuel leak approximately 30 minutes after launch. SpaceX announced that its ground test of a new Block 3 booster ended in an explosion in late 2025, requiring the rapid construction of a replacement. This pattern of progress, punctuated by failures, is not evidence of incompetence. It is the methodology that produced Falcon 9's extraordinary reliability. SpaceX tests aggressively, accepts failures as learning opportunities, and iterates at a pace that legacy aerospace companies find impossible to match. The trajectory of improvement across Starship's test campaign is undeniable. But it is also important to note that as of early 2026, Starship has not yet achieved full orbital flight, has not demonstrated orbital refueling between 2 separate vehicles, has not flown the Block 3 configuration that SpaceX considers necessary for Mars-class missions, and has not conducted any demonstration mission beyond Earth orbit. The vehicle is progressing rapidly. It is also years away from operational Mars capability. This track record gave credibility to claims that would otherwise sound delusional. When Musk outlined his Mars architecture in a detailed presentation to SpaceX employees in May 2025, the plan followed a logical progression built on demonstrated capabilities. 5 uncrewed Starships would launch toward Mars during the 2026 transfer window, carrying approximately 10 metric tons of useful payload each. These initial ships would test the landing procedures, gather surface data, and prove that Starship could survive the Martian entry, descent, and landing sequence, which is considerably more challenging than landing on Earth due to the thin Martian atmosphere that provides minimal aerobraking, but still generates significant heating during entry at interplanetary velocities. The entry, descent, and landing challenge on Mars is worth understanding because it illustrates the gap between current capability and Mars readiness. Mars has enough atmosphere to generate dangerous aerodynamic heating during entry, but not enough to provide significant deceleration. Earth's thick atmosphere slows incoming vehicles from orbital velocity to subsonic speeds using aerodynamic drag alone. Mars's atmosphere, at less than 1% of Earth's surface pressure, slows vehicles only partially. The result is that any vehicle landing on Mars must use a combination of aerodynamic braking, supersonic parachutes, and powered descent to reach a safe touchdown velocity. Every successful Mars landing to date, from Viking in 1976 through Perseverance in 2021, has used vehicles weighing at most about 1 metric ton. Starship, landing on Mars with payload, would weigh approximately 100 to 200 metric tons. No vehicle of that mass has ever attempted to land on Mars. The physics is different at that scale. The supersonic parachutes that work for 1-ton landers cannot be scaled to vehicles of this mass. Starship would need to rely entirely on propulsive braking, firing its Raptor engines against the direction of travel to slow itself for a controlled touchdown. This has been done on Earth but never on Mars, where the lower gravity, thin atmosphere, and different aerodynamic environment create a completely different engineering problem. SpaceX has discussed heat shield testing under simulated Martian atmospheric conditions, but has not yet demonstrated the complete entry, descent, and landing sequence at Mars. If those initial test landings succeeded, 20 more Starships would follow during the 2028 window. Most would carry Tesla Optimus robots designed to begin constructing ground infrastructure and surveying for water ice deposits. At least one of those 2028 ships would carry human passengers, the first people on Mars. From there, the fleet would scale aggressively. 100 ships in 2031, 500 in 2033, eventually 1,000 to 2,000 ships per Mars transfer window, each carrying 100 to 200 passengers. The arithmetic sounds almost reasonable when you lay it out this way. If each crewed starship carries 100 people, and you send 1,000 ships every 26 months, you could theoretically deliver 100,000 people to Mars per transfer window. At that sustained rate, reaching 1 million inhabitants would take roughly 26 years of maximum operations. Musk himself acknowledged the timeline would stretch across decades, but he framed it as achievable within a single human lifetime. A city on Mars by the 2050s or 2060s, the first self-sustaining civilization beyond Earth. Multiple credible aerospace engineers and former NASA officials reviewed the broad architecture and found the transport concept sound. Robert Moses, a retired aerospace engineer from NASA's Langley Research Center in Virginia, described the SpaceX Mars plan favorably compared to NASA's own design reference architecture for human Mars missions. The physics of getting to Mars using Starship is real. The propulsion system works. The orbital mechanics check out. The methane propellant concept for in-situ resource utilization is grounded in established chemistry. The refueling concept, while still undemonstrated at scale in orbit, rests on principles that have been validated in smaller-scale testing. Donald Rapp, a chemical engineer and consultant for NASA's Jet Propulsion Laboratory, noted the logistical challenges of orbital refueling, but acknowledged the concept was sound in theory. No serious engineer disputes that SpaceX has the talent and institutional velocity to develop a vehicle capable of reaching Mars. But here is where the dream begins to fracture along a fault line that most people do not notice. Everything SpaceX has described, every timeline, every fleet-size projection, every architectural diagram, every presentation to employees and investors addresses one specific problem: getting mass from the surface of Earth to the surface of Mars. That is a transportation problem, and SpaceX is perhaps the greatest transportation company in the history of spaceflight. They may genuinely solve it. They may land cargo on Mars within the next few years. They may land humans on Mars before the end of this decade. They may establish a foothold, a research station, an outpost. None of that is a city. The word city implies something fundamentally different from a base or an outpost. It implies permanence that extends across human lifetimes and beyond. It implies self-sufficiency at a level where the community generates everything it needs from internal resources. It implies a population large enough and diverse enough to sustain itself biologically through reproduction across generations without genetic bottlenecks. It implies industry capable of manufacturing every critical tool, component, and material. It implies agriculture that reliably feeds the entire population year after year without Earth imports. It implies medical systems that handle the full spectrum of human health needs, from prenatal care through geriatric medicine. It implies education systems that transmit the accumulated knowledge and skills of civilization to each new generation with sufficient depth to maintain every critical profession. It implies governance that maintains social order, resolves disputes, and makes collective decisions about resource allocation. It implies culture that gives life meaning beyond mere biological survival. SpaceX's entire public architecture describes how to deliver things to Mars. It does not describe how to build a civilization once those things arrive. And that gap between delivery and civilization is not a detail to be worked out later by some future generation of urban planners and social engineers. It is the core problem. It is the hardest problem. And it is the problem that has received the least serious public attention relative to its difficulty. Consider an analogy. The standardized shipping container revolutionized global trade when it was introduced in the 1950s. Those simple steel boxes made it possible to move goods across oceans cheaply and efficiently, transforming the global economy. But the shipping container did not build Shanghai. It did not create the electrical grid, the water treatment plants, the hospitals, the semiconductor fabs, the schools, the courts, the farms, the banks, or the social institutions that make a city of 28 million people function. The container moved things. The city required everything else. SpaceX is building the most powerful shipping container ever made. But a shipping container is not a city, and the distance between Mars and Earth makes that distinction not merely important, but existential. Even SpaceX seemed to acknowledge this when, in February 2026, the company told investors it was deprioritizing Mars in favor of lunar missions. The Wall Street Journal reported that SpaceX had abandoned plans for a Mars mission in 2026, instead targeting an uncrewed lunar landing demonstration as soon as March 2027. Musk announced the strategic shift publicly, explaining that the moon offered faster iteration cycles because you can launch to the moon every 10 days with a 2-day trip time, while Mars windows open only every 26 months with a 6-month transit. A lunar settlement could potentially be achieved in under a decade. A Mars settlement would take more than 20 years. The man who had spent 2 decades telling the world that the moon was a distraction from Mars was now telling the world that Mars was being deferred in favor of the moon. This was not a failure of ambition. It was not a funding problem. It was not evidence that SpaceX is lying or that Musk is a fraud. It was a collision with physical reality that even the most capable engineering organization in the world cannot overcome through willpower and iteration speed alone. The challenge of Mars is not reaching the surface. The challenge is everything that happens after you land, and everything that happens after you land has almost nothing to do with rockets. It is worth noting that Musk's Mars timeline has shifted repeatedly over the years, always in the direction of delay. In 2016, he announced plans to send an uncrewed Red Dragon capsule to Mars by 2018 and discussed crewed missions by 2024. In 2017, he shifted to Starship and pushed the uncrewed target to 2022. In 2020, he said he was highly confident humans would land on Mars by 2026. By 2024, the crewed mission target had been pushed to no earlier than 2029. By May 2025, uncrewed cargo missions were described as having a 50-50 chance for the 2026 window, with crewed flights no earlier than 2029 and more likely 2031. By early 2026, Mars was formally deprioritized for 5 to 7 years. Each delay is individually understandable. Rockets are hard. Testing reveals problems. Problems require redesign. Redesign takes time. But the pattern is also informative. It suggests that the actual difficulty of reaching Mars, let alone building on it, consistently exceeds even informed expert estimates. And reaching Mars is supposed to be the easy part. The disconnect between transport and settlement has historical parallels that make the point vividly. In the 15th and 16th centuries, the caravel and the carrack were revolutionary ships that enabled European exploration of the Americas. These vessels could cross the Atlantic Ocean reliably. They could deliver people, supplies, and equipment to the New World. They were the starships of their era, the transport technology that made a new frontier accessible. But the ships did not build Jamestown. The ships did not create the agricultural systems, the governance structures, the trade relationships, the legal frameworks, or the industrial capacity that eventually turned scattered colonial outposts into functioning cities and then into a new civilization. That process took centuries. It required millions of people. It required the development of new institutions tailored to new conditions. It required adaptation, failure, death on an enormous scale, and slow, painful learning that could not be accelerated by building faster ships. The ships were necessary. They were not sufficient. There is another dimension to this gap that deserves attention. SpaceX is a private company. Its revenue comes primarily from commercial satellite launches, Starlink internet service, and NASA contracts for crew and cargo delivery to the International Space Station and for the Artemis human landing system. These are real, profitable business lines that sustain the company's operations, but they are fundamentally Earth-centric revenue streams. Building a city on Mars generates no revenue. It consumes capital on an extraordinary scale without any identified mechanism for return on investment. Musk has spoken about funding Mars settlement through Starlink profits and through the increasing valuation of SpaceX as a company, but this amounts to subsidizing the most expensive civil engineering project in human history from the profits of an internet service provider. The economics do not close. They depend on sustained willingness by investors and leadership to pour tens or hundreds of billions of dollars into an endeavor that produces no financial return for decades or longer. History suggests that such sustained philanthropic commitment to mega projects without economic justification is exceedingly rare and almost never survives changes in leadership, economic downturns, or shifting public priorities. The February 2026 announcement was not just a strategic pivot, it was a tacit acknowledgement that even getting the first steps right requires starting with a closer, easier, more forgiving target. The Moon is 240,000 miles away. Mars is 34 million miles away at its closest approach and 250 million miles at its farthest. The Moon has no atmosphere, which actually simplifies landing in some respects because there are no aerodynamic uncertainties. The Moon has only 1/6 Earth gravity, even less than Mars's roughly 1/3, but its proximity allows rapid testing and iteration of settlement technologies. The Moon can be reached in 2 days, meaning emergency evacuation is theoretically possible. Communication delay to the Moon is about 1.3 seconds each way, enabling near real-time conversation with Earth-based support teams. If SpaceX, with all its demonstrated capability, recognizes that it needs to learn how to build settlements on the Moon first, the honest implication is that a Mars city is not a single engineering challenge away from reality. It is an entire civilization's worth of problems away. What comes next reveals why that gap is vastly wider than most people understand. Words matter enormously when we talk about humans on Mars. The specific language determines whether we are discussing something achievable within decades or something that may require centuries of sustained effort. The space industry, the media, and the public routinely blur 4 distinct concepts into a single vague narrative about colonizing Mars: a crewed mission, a small outpost, a permanent base, and a self-sustaining city. These are not points on a single smooth spectrum that you gradually slide along as you add more cargo flights. They are fundamentally different endeavors separated by orders of magnitude in complexity, cost, time, and unsolved engineering problems. A crewed mission to Mars is the simplest of the 4, and even calling it simple is deeply misleading given that no one has ever done it. A crewed mission means sending a small group of astronauts, probably between 4 and 12 people, to the Martian surface for a limited stay. The duration is dictated by orbital mechanics. Because of how Earth and Mars orbit the Sun, the most efficient trajectory uses a Hohmann transfer that requires roughly 6 months of transit time in each direction. Once you arrive at Mars, you must wait approximately 500 days for the planets to realign before you can return efficiently. This means a total mission duration of roughly 2.5 years. The crew lives in their landing vehicle or a pre-deployed habitat shipped in advance. They carry essentially everything they need from Earth, or rely on a small amount of in-situ resource utilization, perhaps extracting oxygen from the Martian atmosphere using a device similar to the MOXIE experiment that flew on the Perseverance rover and successfully produced oxygen from carbon dioxide in 2021. At the end of their stay, they launch back to Earth using fuel manufactured from Martian resources or carried with them. The habitat is either abandoned or left dormant for the next crew. This is what NASA's Design Reference Architecture 5 describes. This is what Apollo was to the Moon. It is exploration. It is potentially historic. And it is the only category of Mars activity that anyone has come close to being technically capable of executing within the next decade or 2. A small outpost extends the concept in an important but incremental way. Instead of abandoning the habitat after each mission, you build something that persists between crew rotations. Power systems stay on during the gap between visits. Equipment accumulates on the surface. Each visiting crew adds to the infrastructure left by the previous team. Think of it as the International Space Station model transplanted to the Martian surface. The outpost supports perhaps 6 to 20 people at any given time. It depends entirely on Earth for resupply of food, spare parts, medical supplies, complex equipment, and critical consumables. If the resupply missions stop, the outpost is abandoned or the crew faces eventual death from resource depletion. This is what SpaceX's near-term Mars plans actually describe in operational terms, even if the aspirational language surrounding them suggests something grander. The 5 uncrewed starships proposed for the 2026 window and the 20 crewed ships for 2028 describe the seed of an outpost, not the foundation of a city. A permanent base represents a meaningful step beyond an outpost, but it remains fundamentally tethered to Earth. A base implies continuous habitation with no planned period of abandonment. It houses dozens to perhaps a few hundred people. It produces some of its own resources: oxygen extracted from the atmosphere, water melted from subsurface ice deposits, perhaps basic construction materials processed from regolith, maybe even some food grown in pressurized greenhouses. But the base still depends on Earth for high-technology components, advanced medical supplies, replacement electronics, specialized chemicals, complex food inputs, and the deep expertise needed to diagnose and solve novel problems. When something breaks that the crew cannot fix with the tools and materials on hand, they wait for the next transfer window to receive the necessary parts from Earth. The closest terrestrial analogy is McMurdo Station in Antarctica. McMurdo houses over 1,000 people during the austral summer season. It has dormitories, laboratories, a fire station, 3 airstrips, a harbour, a power plant, water and wastewater treatment facilities, a general store, a barber shop, and even a chapel. McMurdo is the largest community in Antarctica. It has operated continuously since 1956, nearly 70 years of uninterrupted presence. And McMurdo is not self-sustaining, not even close. It receives regular supply flights and annual ship deliveries of fuel, food, equipment, and construction materials. If those supply lines were permanently severed, McMurdo would be evacuated because it cannot survive independently. It exists in an environment that is vastly more hospitable than Mars. Antarctica has breathable air. It has liquid water available through ice melting. It has Earth gravity. It has magnetic field protection from cosmic radiation. Its temperatures, while extreme, are hundreds of degrees warmer than a Martian winter night. Even the coldest recorded temperature on Earth, approximately -89 degrees Celsius at Vostok Station, is warmer than typical Martian nighttime conditions at many locations. 70 years of continuous operation in a comparatively benign environment has not produced self-sufficiency. The implications for Mars should give everyone pause. A self-sustaining city is something else entirely. It means a population large enough to maintain genetic diversity, social complexity, and division of labor sufficient for a functioning industrial civilization. It means the ability to produce every critical input for survival without Earth, every molecule of breathable atmosphere, every calorie of food, every liter of drinking water, every watt of electrical energy, every replacement part for every machine, every medication for every treatable illness, every surgical instrument, every semiconductor chip, every structural beam, every pane of glass, every meter of wire, every square meter of fabric, every gasket, seal, bolt, bearing, sensor, valve, pump, filter, motor, and fastener that a modern technological society requires to function day after day, year after year, decade after decade. A city means that if Earth vanished tomorrow, if every supply ship was cancelled forever, the people on Mars would not merely survive for a few desperate months by rationing their stockpiles. They would continue to exist as a functioning civilization. They would continue to grow food in quantities that feed their entire population, plus a surplus for growth. They would continue to manufacture the tools and equipment they need to maintain their infrastructure. They would continue to maintain and expand their habitable volume as the population grows. They would continue to educate their children in the full range of technical and professional disciplines needed to sustain the settlement. They would continue to provide comprehensive medical care, including surgery, pharmaceuticals, and treatment for chronic conditions. They would continue to reproduce successfully and raise healthy children. They would continue to innovate and solve problems that have not yet been anticipated. They would do all of this indefinitely, across generations, without any external input whatsoever. That is the claim that has been attached to SpaceX's Mars vision. Not a base, not an outpost, a self-sustaining city of 1 million people. And the distance between a permanent Antarctic-style base and a self-sustaining industrial city is arguably greater than the distance between having no presence on Mars at all and having a permanent base. Let us examine the cargo mathematics to see why. Musk has estimated that building a functioning city on Mars requires delivering roughly 1 million metric tons of useful cargo to the Martian surface. He arrived at this figure by estimating the per-person mass requirements for a functioning settlement at roughly 1 metric ton per person, and multiplying by a target population of 1 million. At Starship's projected reusable payload capacity of approximately 100 metric tons to Mars, delivering 1 million tons requires 10,000 fully loaded Starship flights. If SpaceX achieves its most ambitious launch cadence of 1,000 ships per transfer window, delivering the full 1 million tons would take 10 transfer windows, spanning roughly 20 years of sustained maximum operations. These figures collapse into absurdity when you examine the supporting logistics. Each Starship bound for Mars must first reach low Earth orbit and then be refueled by multiple tanker flights before firing its engines for the Mars injection burn. Current estimates suggest each Mars-bound Starship requires between 6 and 12 tanker launches to completely fill its propellant tanks in orbit. The exact number depends on how much propellant boils off during the fueling process and how efficiently the cryogenic fluids transfer between vehicles in microgravity, processes that have never been demonstrated at scale. Donald Rapp of NASA's Jet Propulsion Laboratory estimated that at 12 tanker launches per Mars-bound ship, sending 5 Starships to Mars in the 2026 window would require 60 tanker launches. Sending 1,000 ships would require 6,000 to 12,000 tanker launches in the months preceding the transfer window. That means 30 to 60 launches per day, every single day, for 6 to 12 months straight. SpaceX's current record is approximately 165 Falcon launches in a single calendar year. The required cadence represents a 35-fold to 70-fold increase over current maximum operations sustained without interruption, with near-zero failure rates using ground infrastructure that does not yet exist. Even if you grant these assumptions generously, the transfer window problem introduces a vulnerability that cannot be engineered away. Mars and Earth align for efficient transfers only once every 26 months. Miss the window and you wait more than 2 years for the next opportunity. There is no express lane, there is no shortcut. Orbital mechanics does not negotiate. The transfer window itself is not an instant, but a period of several weeks during which launches must occur to achieve acceptable transit times and fuel efficiency. Outside this window, reaching Mars requires dramatically more fuel, longer transit times, or both, making off-window flights prohibitively expensive even by the standards of interplanetary travel. Every piece of cargo, every person, every emergency medical supply, every critical replacement component must either arrive during the narrow launch period or wait more than 2 years for the next chance. If a habitat on Mars suffers a catastrophic pressure failure and the spare structural seals are on the next supply manifest, the residents do not get a rush delivery. They either fix the problem with what they have or they die. If an epidemic breaks out and the needed antiviral is not in stock, they wait 26 months. If a key piece of agricultural equipment fails, and the replacement circuit board requires a component not available on Mars, they wait 26 months. If a pregnant woman develops a complication requiring a medication that has expired and cannot be synthesized locally, she waits 26 months. This is not a temporary inconvenience of early settlement that will be solved as the base matures. It is a permanent feature of Mars's orbital position relative to Earth. No amount of rocket development changes the geometry of the solar system. For comparison, consider how dependent even well-established remote communities on Earth are on regular supply chains. When the research expedition vessel MV Akademik Shukalski became trapped in Antarctic sea ice in December 2013, carrying scientists, tourists, and journalists, an international rescue operation involving icebreakers and helicopters from multiple nations was mounted within days. When a medical emergency occurs at the Amundsen Scott South Pole Station during the winter months when flights are impossible, personnel must wait months for evacuation, and several people have died as a result. The South Pole Station is roughly 800 miles from McMurdo and approximately 2,500 miles from the nearest major hospital in New Zealand. Mars is, at minimum, 34 million miles from Earth. The isolation is not merely quantitatively different, it is qualitatively different. It transforms every supply dependency from a logistical inconvenience into an existential risk. The communication delay multiplies this isolation. Depending on the relative positions of the two planets at any given time, one-way radio signals take between approximately 4 and 24 minutes to travel between Earth and Mars. This means no real-time communication is possible. No phone calls, no live video consultations with specialists on Earth, no remote-controlled surgery, no back-and-forth troubleshooting with mission control. Every interaction becomes a series of messages sent and received with round-trip delays of 8 to 48 minutes. In an emergency where minutes matter, an expert on Earth who knows how to fix the problem is effectively unreachable. Consider food production at city scale. A crew of 12 on a limited duration mission can bring all their food from Earth. Freeze-dried, vacuum-sealed, carefully rationed, perhaps supplemented by a small greenhouse experiment growing lettuce and radishes as much for morale as for nutrition. The mass penalty is significant, but manageable within a mission framework. A city of 10,000 people requires roughly 30 million calories per day. Producing this on Mars requires large-scale agriculture in pressurized, heated, artificially illuminated greenhouses operating year-round without interruption. The plants need water, mineral nutrients precisely balanced for each crop, carbon dioxide supplementation at concentrations optimized for photosynthesis, pollination management using either mechanical systems or carefully maintained insect populations, pest and disease control in a closed ecosystem where a single invasive fungus or bacteria could devastate the food supply, and growing media that is either manufactured from Martian regolith after painstaking removal of toxic perchlorates, or brought from Earth in quantities that would consume enormous payload capacity. The greenhouses themselves represent enormous engineering challenges. They must withstand the pressure differential between their interior Earth-like atmosphere at roughly 101,000 pascals and the near vacuum outside at 600 pascals. They must provide thermal management against temperature swings that can exceed 100 degrees Celsius between day and night. They must protect plants from ultraviolet radiation that penetrates the thin Martian atmosphere at levels lethal to many terrestrial crops. They must be large enough to feed thousands of people, which means hundreds of thousands of square meters of growing area given realistic crop yields. And they must be constructed, maintained, expanded, and eventually replaced using materials and tools manufactured locally, because the alternative is importing greenhouse components from Earth at costs that would make every head of lettuce worth more than its weight in gold. Crop diversity presents an additional complication. Humans require a varied diet for nutritional completeness. Relying on a small number of staple crops creates vulnerability to disease, pest outbreaks, and nutritional deficiencies. A sustainable agricultural system must include grains, legumes, vegetables, fruits, and ideally some animal protein from aquaculture or poultry. Each crop and animal species requires different growing conditions, different nutrient inputs, different environmental controls, and different expertise to manage. The agricultural knowledge base needed to feed a city on Mars encompasses agronomy, soil science, hydroponics, aquaponics, plant pathology, entomology, animal husbandry, food processing, food preservation, and nutrition science. This knowledge cannot simply be downloaded from a database. It requires trained practitioners who understand how to diagnose problems, adapt techniques to novel conditions, and solve unexpected challenges as they arise. NASA has studied closed-loop agricultural systems for decades. The most ambitious attempt to create a self-sustaining closed ecological system on Earth was Biosphere 2, a 3.14-acre sealed glass and steel structure constructed in the Arizona desert between 1987 and 1991 at a cost of approximately $150 million. 8 crew members sealed themselves inside in September 1991 for a planned 2-year mission. They had every conceivable advantage: Earth gravity, natural sunlight through the glass enclosure, Earth normal temperatures on the exterior preventing thermal cycling stress on the structure, carefully designed biomes including a rainforest, an ocean, a savanna, a marsh, and agricultural areas. The system had been designed by some of the world's leading ecologists and environmental engineers, and it failed. Oxygen levels inside Biosphere 2 dropped from the normal 21% to a dangerous 14% within 16 months, equivalent to conditions at an altitude of roughly 4,300 meters. The cause was traced to soil microorganisms consuming oxygen faster than the plants could regenerate it, combined with carbon dioxide being absorbed by the concrete structure. The crew suffered from chronic hunger due to agricultural yields far below projections. Pollinating insects died off, threatening crop reproduction. Pest species including ants and cockroaches proliferated in the absence of natural predators. Social conflict among the 8 crew members became severe under the stress of hunger, oxygen deprivation, and confinement. Emergency oxygen injections from outside were required to keep the crew alive. The experiment demonstrated that creating and maintaining a stable, closed ecological system is extraordinarily difficult, even under conditions incomparably more favourable than Mars. The designers had access to natural sunlight, Earth gravity, stable external temperatures, breathable air as an emergency backup, and the ability to walk away if conditions became truly dangerous. Mars offers none of these safety margins. If humanity's best attempt at closed-loop ecology for 8 people on Earth required emergency intervention to prevent crew death, the prospect of maintaining closed ecological systems for tens of thousands of people on Mars without any possibility of external intervention deserves the most serious skepticism. Water recycling presents similar challenges at city scale. The International Space Station's environmental control and life support system achieved a milestone of 98% water recovery in 2023 after NASA added a brine processor assembly to extract remaining water from urine distillation byproducts. Before that upgrade, recovery stood at roughly 93 to 94%. Even at 98%, the remaining 2% must be resupplied from Earth, and the system itself requires regular replacement of filters, chemical beds, catalysts, and mechanical components that cannot be manufactured in orbit. The ISS supports a crew of 6 to 12 people in a vehicle that cost over $100 billion to build and maintain. Scaling water recycling to a city of thousands or tens of thousands requires achieving closure rates even higher and sustaining them for decades. Because at city scale, even a 2% loss compounds into tons of unrecoverable water per year, in an environment where shortfalls cannot be replenished from rainfall, rivers, or aquifers. Mars does have water ice, confirmed by both orbital observations and surface measurements from multiple missions, including the Phoenix lander, the Mars Reconnaissance Orbiter, and the Curiosity and Perseverance rovers. Subsurface ice deposits exist at mid-latitudes and become more abundant toward the poles. Extracting this ice requires identifying accessible deposits, developing mining equipment capable of operating in Martian conditions, building infrastructure to transport ice to the settlement, and constructing purification and distribution systems. The mining operation itself presents challenges. Martian ice may be mixed with regolith, requiring separation processes. It may be buried under meters of frozen ground, requiring drilling or excavation equipment. The mines must be powered, maintained, and eventually expanded as the settlement's water needs grow. Every component of this water supply chain must be maintainable using locally available resources and expertise over the long term. Atmosphere management is perhaps the most immediately life-critical challenge of all, because the consequences of failure are measured in minutes rather than weeks or months. Every habitable space on Mars must be a sealed pressure vessel. The Martian surface is a near vacuum, with an atmosphere toxic to humans. A person standing unprotected outside would die within minutes. Every wall, every window, every airlock, every connection point between modules must maintain a 14.7 pounds per square inch pressure differential against near vacuum. A puncture in a habitat wall the size of a pencil would cause rapid depressurization of the affected module. The air inside would rush out into the near vacuum with explosive force. Anyone in the module who could not reach an airlock and seal it within minutes would die. The atmosphere inside the habitat must be continuously managed. Humans consume oxygen and exhale carbon dioxide. Without active removal, carbon dioxide concentrations rise to dangerous levels within hours. In a sealed environment, the carbon dioxide must be scrubbed from the air and either vented or recycled. Oxygen must be continuously generated, either through electrolysis of water or through chemical processes using atmospheric carbon dioxide. Nitrogen, which makes up roughly 78% of Earth's atmosphere and serves as an inert buffer gas that prevents the fire hazard of a pure oxygen environment, must be sourced and maintained. Trace contaminants from human metabolism, off-gassing from materials, and chemical processes must be filtered and neutralized. Humidity must be controlled to prevent both respiratory discomfort and condensation that can damage equipment and promote microbial growth. Temperature must be regulated. All of these processes must operate continuously, redundantly, and reliably for decades without interruption and without replacement components from Earth. Over time, as habitable volume expands to city scale, the total surface area of pressurized structures grows enormously, and with it the probability that seals, welds, and joints will develop leaks that must be detected and repaired before they become catastrophic. Energy production at city scale deserves special attention because every other system depends on it. A Mars settlement needs power for heating, because without continuous thermal management, interior temperatures would plummet to lethal levels within hours. It needs power for atmosphere processing, running the compressors, heaters, chemical reactors, and fans that keep the air breathable. It needs power for water extraction and purification. It needs power for lighting, because greenhouses on Mars cannot rely solely on natural sunlight, which arrives at roughly 43% the intensity received on Earth, and is further reduced during global dust storms that can last months. It needs power for communications, computing, transportation, manufacturing, and every other function. The two realistic power sources on Mars are solar and nuclear fission. Solar panels on Mars produce roughly half the energy per unit area compared to panels on Earth, before accounting for dust accumulation that degrades performance steadily. The global dust storms that periodically engulf Mars can reduce solar input by 90% or more for weeks. The Opportunity rover lost contact in June 2018 when a global dust storm coated its solar panels, and NASA officially declared the mission over in February 2019. A city dependent primarily on solar power must have either enormous battery reserves to survive dust storms or a nuclear backup. Nuclear fission provides reliable power independent of weather, but requires either uranium enrichment capability on Mars or regular importation of reactor fuel from Earth, neither of which currently exists in any form. NASA's Kilopower project demonstrated a small prototype fission reactor in 2018, producing approximately 1 kilowatt of electrical power. A city of 10,000 people might require hundreds of megawatts. Scaling from 1 kilowatt to hundreds of megawatts represents a factor of 100,000, an engineering gap that dwarfs anything in Starship's development history. Construction at scale on Mars introduces problems with no terrestrial precedent. Every inhabited structure is a pressure vessel maintaining Earth normal atmospheric pressure against an external near vacuum. Structural failure in a Mars habitat means explosive decompression, not the slow degradation that characterizes building failures on Earth. Building materials must come from either Earth at prohibitive cost or from local Martian resources through extraction, processing, and manufacturing chains that must be built from scratch. Iron is abundant in Martian regolith, but extracting metallic iron from iron oxide rock requires smelting infrastructure, reducing agents, and enormous energy. Researchers have proposed sulfur-based Martian concrete using sulfur deposits as a binder, but this material has never been used for pressurized construction and has very different structural properties than conventional concrete. Every construction material pathway — steel, glass, concrete, polymer, composite — requires its own dedicated mining, processing, and manufacturing chain. Consider what the settlement actually looks like after the first decade of operations under the most optimistic assumptions. Perhaps 10 to 20 starships have successfully landed on Mars, delivering 1,000 to 2,000 metric tons of equipment and supplies. A crew of 50 to 100 people has established a habitat cluster, deployed solar arrays, and begun extracting water from subsurface ice. They are alive. They are productive. They are conducting groundbreaking science. This represents one of the greatest achievements in human history. It is also, by every meaningful definition, a research outpost. It depends entirely on Earth for resupply, replacement parts, medical support, and the expertise of thousands of engineers and scientists on Earth who monitor systems remotely and design solutions to problems as they arise. Remove the Earth connection permanently, and this outpost has a finite lifespan measured by the rate at which its stockpiled consumables deplete and its equipment fails without replacement. This is the gap that no amount of launch vehicle performance can bridge by itself. Everything that SpaceX has publicly described, every presentation, every timeline, every fleet projection, addresses one step in this process: getting mass from Earth to the surface of Mars. The company has discussed Starship's payload capacity, its refueling architecture, its landing procedures, its manufacturing cadence at Starbase. These are real engineering achievements backed by demonstrated progress. But they describe the delivery truck, not the city. They describe how to bring building materials to a construction site, not how to build a civilization with those materials in an environment that is actively trying to kill everyone who lives there. But the challenges of building on Mars go far deeper than logistics. The physical environment itself makes even the concept of long-term habitation scientifically uncertain. Every planet in the solar system is trying to kill you. Mars is simply more polite about it than most. The red planet does not announce its hostility with crushing atmospheric pressure like Venus, where surface conditions would flatten and melt any human vehicle within hours. It does not scream with radiation belts like Jupiter, where the charged particle environment would deliver a lethal dose to an unshielded human in minutes. Mars looks almost welcoming in photographs sent back by rovers and orbiters. Rust-coloured deserts stretching to the horizon, familiar geological features, canyons deeper than the Grand Canyon, volcanoes taller than any mountain on Earth, dried riverbeds that whisper of a warmer, wetter past, a day that lasts only 37 minutes longer than Earth's, a tilt on its axis almost identical to Earth's, giving Mars recognizable seasons. This visual familiarity is profoundly dangerous because it obscures physical realities that make long-term human habitation fundamentally uncertain in ways that have nothing to do with rocket engineering. Begin with radiation, which represents perhaps the most thoroughly documented threat. Earth's inhabitants enjoy protection from two overlapping shields that Mars lacks entirely. The The first is a global magnetic field generated by convection currents in Earth's liquid iron outer core. This magnetosphere extends tens of thousands of kilometers into space, deflecting the constant stream of charged particles blown outward by the sun, known as the solar wind, and channeling them toward the magnetic poles where they create the spectacular aurora borealis and australis. This invisible shield also provides partial protection against galactic cosmic rays, the extremely high-energy particles that originate outside our solar system from sources like supernovae and active galactic nuclei. Mars lost its global magnetic field approximately 4 billion years ago, when its smaller core cooled and solidified, shutting down the dynamo that generates the field. Without this invisible armor, the solar wind has been stripping away the Martian atmosphere for eons, thinning it to the wispy remnant that exists today. The second shield is Earth's atmosphere itself. At sea level, you sit beneath a column of air with a mass equivalent to roughly 10 meters of water. This atmospheric mass absorbs and scatters incoming charged particles and electromagnetic radiation before they reach the surface. The combination of magnetosphere and atmosphere keeps cosmic ray exposure on Earth's surface to a fraction of a millisievert per year. Including all natural and medical sources, the average person on Earth receives a total dose of roughly 6 millisieverts annually. On the surface of Mars, the radiation environment is dramatically different. Measurements from the radiation assessment detector aboard the Curiosity rover, which has been operating on Mars since August 2012, recorded a steady-state surface dose rate of approximately 0.67 millisieverts per day from galactic cosmic rays, with additional spikes during solar particle events. That baseline translates to roughly 245 millisieverts per year, nearly 40 times the average annual exposure on Earth's surface. The transit between Earth and Mars adds a substantial additional dose. Outside Earth's magnetosphere, spacecraft are exposed to the unshielded deep space radiation environment. Research published in 2025 in the journal NPJ, Microgravity, validated radiation exposure models from Earth to Mars using data from instruments aboard the Artemis 1 mission spacecraft, the Biosentinel CubeSat, and the International Space Station. The study confirmed that computational predictions match actual measurements to within 4 to 25% across diverse shielding configurations. The models work, the physics is well characterized, and the numbers describe a radiation environment that places fundamental, non-negotiable constraints on how long humans can safely remain on Mars. NASA recently updated its career radiation exposure limit to 600 millisieverts, calculated to cap the mean excess risk of cancer-related death at 3% above baseline. This limit was designed to be more equitable than previous limits, which varied by age and sex, but it remains a compromise between enabling exploration and protecting health. A standard Mars mission lasting approximately 2.5 years, including 6 months of transit each way and roughly 500 days on the surface, would expose astronauts to cumulative doses that approach or likely exceed this career limit, depending on the phase of the solar cycle and the specifics of the spacecraft and surface habitat shielding. Solar minimum, when the sun's magnetic field is weakest and provides the least deflection of galactic cosmic rays, produces the highest radiation environment. Unfortunately, solar minimum also corresponds to the lowest frequency of dangerous solar particle events, creating an optimization dilemma. You face less acute risk from solar storms, but more chronic risk from cosmic rays. A 2025 NASA technical report from the agency's Moon to Mars Radiation Protection Program explicitly noted that Mars missions are expected to exceed the 600 millisievert career limit, and that the agency is pursuing a multi-layered protection strategy including spacecraft shielding, storm shelters, real-time dosimetry, forecasting systems, and emerging biological countermeasures to manage the risk. The report acknowledged that combined uncertainties from interacting spaceflight stressors affect risk projections for cancer, central nervous system function, cardiovascular health, and immune regulation, meaning that even current risk estimates may understate the true danger. For a visiting crew of trained astronauts on a single Mars mission, radiation is a manageable and accepted risk. You consent to an elevated lifetime probability of cancer and cardiovascular disease in exchange for the extraordinary achievement of walking on another world. Astronauts have always accepted elevated risks. That is the nature of exploration. But a city is not a crew rotation. A city contains people who will live on Mars for decades. People who will never return to Earth. Children who will be born and grow up under constant radiation exposure, 40 times higher than any population on Earth has ever experienced. Pregnant women whose developing fetuses are exquisitely sensitive to ionizing radiation during critical developmental windows. Elderly residents whose already elevated baseline cancer risks would be compounded by decades of Martian radiation exposure. The question for a city is not whether a healthy 35-year-old astronaut can tolerate 2 years of elevated radiation. The question is whether a diverse population spanning all ages and health conditions can thrive across multiple generations under chronic exposure at these levels. Shielding is the obvious answer, but it introduces complications that are not immediately apparent. Research conducted at NASA's Langley Research Center demonstrated that on the Martian surface, adding conventional aluminum shielding to a habitat can actually increase the total radiation dose to inhabitants. The mechanism is secondary particle production. When extremely high-energy galactic cosmic ray nuclei, particularly the heavy ions that represent 1% of cosmic ray flux but cause a disproportionate share of biological damage, strike dense metal shielding, they fragment into cascades of secondary particles including neutrons. These secondary particles can be more biologically damaging per unit of energy than the original cosmic ray. The result is counterintuitive and troubling. The intuitive response of piling metal over your head makes the problem worse, not better. The most effective shielding strategy on Mars likely involves burying habitats under several meters of regolith. Martian soil provides mass shielding that attenuates radiation through multiple layers of relatively light nuclei, minimizing the secondary particle problem. NASA research suggests that approximately 3 meters of regolith would reduce the radiation dose to levels roughly comparable to what astronauts experience on the International Space Station, which itself is higher than ground-level exposure on Earth, but within manageable bounds for adults. However, excavating and piling 3 meters of soil over pressurized habitats at city scale represents an enormous construction challenge. It requires heavy excavation equipment, transport vehicles and structural engineering to ensure that the weight of the regolith does not compromise the integrity of the pressurized habitat below. In the early phases of settlement, when heavy equipment is scarce and every machine was shipped from Earth at enormous cost, large-scale regolith shielding may not be achievable for all habitable volumes. Even with optimal shielding, galactic cosmic rays cannot be completely eliminated with any practical amount of passive shielding material. The highest energy galactic cosmic ray particles carry energies that would require meters of lead to fully stop masses that are completely impractical for habitat construction. Active magnetic shielding, using powerful superconducting magnets to deflect charged particles, has been proposed in concept studies, but remains entirely theoretical at the scale needed to protect a city-sized settlement. No such system has been built, tested, or demonstrated at any scale. The superconducting magnets required would need to generate field strengths and field volumes far beyond any existing magnet system, while operating reliably for decades in an environment of extreme temperature fluctuations and dust contamination. Pharmaceutical countermeasures, drugs that might protect cells from radiation damage or accelerate DNA repair after exposure, are an active area of NASA-funded research, but do not yet exist in validated form, for the specific mix of radiation types encountered in deep space and on the Martian surface. The interaction between radiation exposure and other spaceflight stressors, including isolation, confinement, sleep disruption, and altered gravity, remains poorly characterized. As noted earlier, the combined uncertainties from these overlapping hazards mean that even current risk models may underestimate the true health burden on long-term Mars residents. The psychological dimension of radiation exposure in a permanent settlement deserves consideration as well. Astronauts on short-duration missions can accept elevated radiation risk as professionals making an informed choice about their own health. Residents of a permanent city, including children who had no say in the decision to bring them into a high-radiation environment, face a different ethical calculus. A city that knowingly exposes its children to radiation levels 40 times Earth normal, with acknowledged but poorly quantified risks of cancer, cognitive impairment, and cardiovascular disease, raises moral questions that are distinct from the engineering questions and equally difficult to resolve. Now layer gravity onto this picture. Mars has approximately 38% of Earth's surface gravity. A person who weighs 80 kilograms on Earth would experience an apparent weight of roughly 30 kilograms on Mars. This sounds liberating, even fun, until you consider what gravity does to the human body at a fundamental level. Every physiological system we possess evolved under Earth's gravitational field over hundreds of millions of years of evolution. Our bones maintain their density by responding to the mechanical loads placed on them by walking, running, standing, and lifting in 1G. Our muscles maintain their mass and strength for the same reason. Our cardiovascular system is exquisitely tuned to pump blood upward against 1G to reach the brain. Our vestibular system, the inner ear mechanism that provides balance and spatial orientation, calibrates itself against a specific gravitational constant. Our lymphatic system depends on gravity-assisted fluid drainage to function properly. We know in extensive detail what happens to the human body in microgravity, because astronauts have lived on the International Space Station continuously for periods ranging from months to over a year. The longest continuous spaceflight by an individual was performed by cosmonaut Valery Polyakov, who spent 437 days aboard the Mir space station in 1994 and 95. More recently, astronauts Scott Kelly and cosmonaut Mikhail Kornienko completed a 340-day mission on the ISS in 2015 and 2016, with Kelly's twin brother Mark serving as a ground-based control subject for the landmark twins study that examined genetic, physiological, and cognitive changes from long-duration spaceflight. The results were instructive and concerning. Bone density loss in microgravity proceeds at approximately 1 to 2% per month, concentrated in weight-bearing bones like the spine, hips, and legs. Muscle atrophy occurs despite aggressive exercise protocols requiring up to 2 hours per day on specialized resistance and cardiovascular equipment. Cardiovascular deconditioning sets in as the heart no longer needs to work against gravity to circulate blood, leading to reduced cardiac output and orthostatic intolerance upon return to gravity. A significant percentage of long-duration astronauts develop spaceflight-associated neuroocular syndrome, a condition involving flattening of the eyeball and swelling of the optic nerve caused by increased intracranial pressure from the headward fluid shift that occurs without gravity. The immune system shows changes resembling accelerated aging. Gene expression patterns shift in ways that are still being catalogued and understood. These effects are partially reversible upon return to Earth gravity, but recovery takes months, and some changes, particularly bone loss in certain skeletal regions, appear to be permanently irreversible even with rehabilitation. What we do not know, and this is the critical gap, is what happens to the human body at 38% gravity over years and decades. No human being has ever experienced Martian gravity for any meaningful duration. The Apollo astronauts spent a maximum of approximately 75 hours on the lunar surface at 16% gravity, a period far too short to observe any physiological adaptation. We have no data, zero data, on what happens to human bones, muscles, cardiovascular systems, immune function, neurological health, or reproductive capacity at 1/3 Earth gravity over periods of years, let alone lifetimes. A NASA technical paper published in 2021 assembled the available indirect evidence and concluded that partial gravity exposure below approximately 0.4 G appears insufficient to maintain musculoskeletal and cardiopulmonary conditioning over the long term. Mars' gravity at 0.38 g falls just below this threshold. The paper emphasized that different physiological systems may respond to partial gravity at different thresholds, making it unlikely that any single gravity level below 1 g can maintain all human systems equally. Exercise countermeasures provide some benefit in microgravity, but have proven insufficient to prevent all physiological deterioration, even with the aggressive 2-hour daily protocols used on the ISS. This uncertainty cascades into existential questions about reproduction and child development that strike at the very foundation of what self-sustaining means. A self-sustaining city requires children. It requires healthy pregnancies carried to full term. It requires healthy infant development through childhood and adolescence. It requires children whose bones, muscles, organs, cardiovascular systems, and nervous systems develop normally enough for them to function as productive, healthy adults capable of maintaining the settlement's infrastructure and having healthy children of their own. This is the non-negotiable requirement that separates a temporary outpost from a permanent civilization, and it is the requirement for which we have the least data and the greatest uncertainty. No mammalian pregnancy has ever been carried to term in anything other than Earth gravity. Experiments with rats and mice in microgravity aboard space stations have produced limited and mixed results, with some studies showing developmental abnormalities in offspring. But microgravity is not Martian gravity. 0g is not 0.38 g. The developmental effects might be entirely different. We simply do not know. We do not know whether a human egg can be fertilized normally in Martian gravity. We do not know whether embryonic development proceeds correctly when the gravitational cues that guide organ positioning and tissue differentiation are 62% weaker than normal. We do not know whether fetal bone mineralization occurs at rates sufficient to produce a viable skeleton. We do not know whether the cardiovascular system of a Martian gestation baby would develop the capacity to function on Earth, or whether Mars-born humans would be physiologically trapped on Mars forever, unable to tolerate the gravity of their ancestral planet. We do not know whether labor and delivery, which depends on gravitational forces assisting the birth process, would proceed safely. These are not edge cases or unlikely scenarios. These are fundamental requirements for species perpetuation that must have clear, positive answers before anyone can credibly claim a permanent multi-generational settlement is feasible. The Martian atmosphere adds layers of hostility that compound these biological uncertainties. 95% carbon dioxide at 600 pascals of pressure, unbreathable, and essentially a vacuum from the standpoint of human physiology. Every breath a Mars resident takes for the rest of their life must come from manufactured atmosphere inside a sealed pressure vessel. Every step outside the habitat requires a full pressure suit that takes time to don, restricts mobility, limits dexterity, reduces sensory input, and creates its own physiological stresses including thermal management challenges, carbon dioxide buildup inside the suit, and physical exhaustion from working against the suit's internal pressure. The psychological implications of this permanent confinement are difficult to overstate and have received far less attention than the engineering challenges. No Mars resident will ever feel unfiltered wind on their face. No Mars resident will ever walk under an open sky and feel rain or sunlight directly on their skin. No Mars child will ever play outdoors in the sense that every child on Earth understands. No resident will ever swim in a natural body of water, hike through a forest, sit by a campfire under the stars, or experience any of the sensory richness that the natural environment of Earth provides and that humans evolved to need for psychological well-being. The entire population lives permanently inside sealed structures with artificial lighting, recycled air, and controlled temperature. Excursions outside require cumbersome pressure suits and are limited in duration and range by suit life support capacity. Submarine crews endure similar conditions of confinement and atmospheric control, but their deployments last months, not lifetimes, and every crew member knows they will eventually surface and return to normal life on Earth. The crews of Antarctic winter overstations experience months of isolation and confinement in harsh conditions, but they too know the isolation is temporary, and that supply flights will resume in the spring. No population in human history has been asked to accept permanent, multi-generational confinement without any possibility of returning to an unconfined natural environment. The closest analogue might be generational prison populations, and the psychological literature on the effects of long-term incarceration does not suggest that confined populations flourish. The psychological toll of permanent confinement, even in comfortable and well-designed habitats, represents a largely unexamined variable in the self-sustaining city equation. It is entirely possible that the psychological demands of permanent Mars residents will prove to be as significant a constraint on city building as radiation, gravity, or industrial self-sufficiency. Temperature extremes assault every structure and material continuously. Mars' surface temperatures average around -60 degrees Celsius globally. Near the equator on a summer afternoon, temperatures might briefly reach a positive 20 degrees Celsius before plummeting to -70 or below overnight. At the poles in winter, temperatures drop below -120 degrees Celsius. Even at the most thermally benign locations near the equator, the daily temperature swing routinely exceeds 80 to 100 degrees Celsius. These thermal cycles stress construction materials in ways that have no terrestrial precedent. Metal expands when heated and contracts when cooled. Over thousands of cycles, this relentless expansion and contraction fatigues welds, works bolted connections loose, and nucleates microfractures that propagate slowly through structural elements over years. Seals made from polymers and elastomers become brittle and crack under repeated thermal cycling, especially at the extreme low temperatures that would be encountered during Martian nights. Adhesives lose their bonding strength. Thermal insulation degrades. Optical coatings on solar panels and windows develop microcracks that reduce transparency and efficiency over time. On Earth, infrastructure engineers design for thermal cycling over ranges of perhaps 40 to 60 degrees Celsius in the most extreme climates, and they have centuries of empirical data on material performance under those conditions. On Mars, the thermal cycling range is double that. The baseline temperature is far colder than anything encountered in routine terrestrial construction, and the material performance data for these specific conditions is essentially non-existent for most construction materials at the scales needed. Materials science for Martian construction is a field in its infancy. Developing, testing, and qualifying materials for pressurized habitat construction under Martian thermal cycling conditions is a multi-decade research program that has barely begun. The Martian regolith itself presents a uniquely insidious chemical threat. Soil samples analyzed by multiple rovers reveal the presence of perchlorates, chlorine-based oxidizing compounds, at concentrations ranging from approximately 0.5 to 1% by weight across tested locations. Perchlorates are toxic to the human thyroid gland, interfering with iodine uptake and hormone production even at low exposure levels. Fine Martian dust particles, many smaller than 10 micrometers and some smaller than 2.5 micrometers, would penetrate habitat seals over time despite best engineering efforts, contaminate indoor air, settle on every surface, and potentially cause respiratory damage similar to, or worse than, silicosis from prolonged inhalation. Martian dust is also strongly oxidizing, meaning it actively degrades organic materials including plastics, rubber, and human tissue on contact. The planet-wide dust storms mentioned earlier can persist for months, coating every external surface with fine abrasive particles that damage solar panels, scratch optical surfaces, clog mechanical joints, and degrade thermal radiators. Then there is the question of medical autonomy, which is perhaps the most underappreciated barrier to true urban permanence on Mars. A city must be able to handle the complete spectrum of human medical needs without any possibility of Earth assistance arriving within a useful time frame. The communication delay of 4 to 24 minutes each way makes real-time telemedicine impossible. The transfer window schedule means physical deliveries of medical supplies can only arrive every 26 months. The distance means emergency evacuation to Earth is not possible. Any medical emergency that cannot be resolved with the resources and expertise present in the settlement is, by definition, a death sentence. Consider what this actually means in practice. It means performing emergency appendectomies with locally trained surgeons using locally sterilized instruments. It means cesarean sections for complicated pregnancies without the option of transferring the mother to a better equipped facility. It means cardiac surgery, including bypass procedures and valve replacements, because heart disease will inevitably affect a population of thousands or tens of thousands over decades. It means comprehensive cancer treatment including surgery, chemotherapy and radiation therapy, because the elevated radiation environment on Mars will drive cancer incidence well above Earth baseline rates. It means psychiatric care for conditions including psychosis, severe depression, and acute anxiety in an environment specifically designed to exacerbate every known psychological stressor: isolation, confinement, interpersonal conflict, monotony, and existential dread. It means neonatal intensive care for premature infants born in an untested gravitational environment. It means dialysis for kidney failure. It means comprehensive dental care, ophthalmology, dermatology, endocrinology, and every other medical specialty that a diverse population requires. Beyond the procedures themselves, a medical system requires consumables: suture material, surgical gloves, antiseptics, anesthetics, antibiotics, analgesics, anticoagulants, contrast agents for imaging, blood products for transfusion, culture media for microbiology laboratories, reagents for chemistry panels. Every one of these consumables must either be stockpiled from Earth in quantities sufficient to last until the next resupply, or manufactured locally using pharmaceutical production capabilities that do not yet exist outside of major industrial economies on Earth. Pharmaceutical manufacturing requires sterile facilities, precisely controlled chemical synthesis or biological fermentation processes, quality assurance testing, and regulatory grade documentation. Building this capability on Mars from scratch represents a project comparable in complexity to establishing the pharmaceutical industry of a small nation. The mental health dimension deserves particular emphasis because it is often treated as secondary to physical survival when in fact it may be the most immediate threat to settlement viability. Extended isolation and confinement studies on Earth, including the Mars 500 simulation conducted by the European Space Agency and the Russian Institute of Biomedical Problems, revealed significant psychological deterioration among crews confined for as little as 520 days, even in comfortable facilities on Earth with the knowledge that they could abort the simulation at any time. Participants experienced depression, lethargy, sleep disturbances, interpersonal conflict, and motivational decline. A Mars settlement offers no possibility of aborting the experience. Residents who develop severe psychological conditions cannot leave. They cannot transfer to a different community. They cannot take a vacation. They are confined permanently in a small, pressurized volume with the same group of people, in an environment where a single emotional breakdown that leads to sabotage of life support equipment could kill everyone. The psychological demands of permanent Mars residents may prove to be as significant a barrier to true city building as any physical or engineering challenge. Every one of these physical barriers — radiation, gravity, uncertainty, atmospheric toxicity, thermal extremes, dust chemistry, psychological confinement, and medical isolation — represents not an engineering inconvenience to be solved with a better design, but a fundamental constraint imposed by the physical nature of Mars itself. A crewed mission can accept these risks with informed consent from a small team of trained professionals who understand they are taking on elevated danger for a limited period. A permanent base can manage them through careful operational protocols, acceptance of elevated health risks, and the understanding that evacuation to Earth remains theoretically possible. But a self-sustaining city must solve every single one of these problems completely, permanently, using locally manufactured solutions, sustained across multiple generations, with no possibility of fallback or evacuation. No rocket addresses any of these challenges. Starship delivers mass to the Martian surface with unprecedented efficiency. It does not generate magnetic fields. It does not create bone density in low gravity. It does not produce breathable atmosphere from toxic air. It does not neutralize perchlorate contaminated soil. It does not treat cancer. It does not deliver babies in an untested gravitational environment. The physical environment of Mars does not care how many metric tons per year you can land on its surface. It cares whether you can keep human beings alive, healthy, and reproductively viable for centuries after they arrive. But even if every one of these physical barriers could somehow be overcome, the challenge would still not be solved. There is a thought experiment that illuminates the true scale of what building a self-sustaining city on Mars actually requires. Imagine you are tasked with building a completely self-sufficient settlement in the most hospitable desert on Earth, the Sonoran Desert in Arizona, perhaps. You have breathable air freely available at 1 atmosphere of pressure. You have liquid water accessible from underground aquifers. You have abundant sunlight and a functional ozone layer. You have Earth gravity. You have temperatures that rarely drop below freezing at your chosen location. You have soil that, with irrigation, can support agriculture. You have paved roads connecting you to the entire global economy within a few hours of driving. Now imagine you must make this settlement permanently, irreversibly independent. No imports of any kind, ever again. No trade, no internet connection to outside expertise, no highway to a hospital, no mail order catalogue, no Amazon delivery. You must mine your own metals, smelt your own steel, manufacture your own electronics from raw materials, refine your own chemicals, produce your own medical equipment and pharmaceuticals, build and repair your own vehicles, generate your own energy, produce your own glass, textiles, plastics, and lubricants, grow and process all your own food, and educate every generation of children in every discipline necessary to sustain a modern technological society forever, with only the people currently living there, without ever receiving anything from outside. No community in human history has ever achieved this. Not in the most hospitable climate on Earth, not on any continent, not at any scale that remotely resembles modern technological civilization. The smallest self-sufficient communities that have existed in human history, isolated Pacific Island populations, remote indigenous groups, certain historical monasteries, sustain themselves at technological levels, orders of magnitude below what we would consider civilized in the modern sense. They had no electronics, no advanced medicine, no power grids, no complex metallurgy, no telecommunications, no industrial chemistry. True self-sufficiency at the technological level required to maintain pressurized habitats, life support systems, and medical facilities on Mars has never been demonstrated by any human settlement anywhere, even under Earth-optimal conditions, and we are proposing to achieve it for the first time on another planet. The industrial requirements for a self-sustaining city defy easy comprehension because modern people have no experience with the depth and complexity of the supply chains that sustain their daily lives. Consider a single object that any resident of a modern city takes for granted: a computer chip. The semiconductor fabrication process requires ultra-clean facilities, where the particle count per cubic meter of air is controlled to levels hundreds of times purer than a hospital operating room. The fabrication sequence involves photolithography using extreme ultraviolet light sources, chemical vapor deposition, ion implantation, chemical mechanical polishing, etching with specialty gases, wafer inspection, dye testing, packaging, and quality assurance. A single modern chip fabrication facility, a so-called fab, costs between $10 and $20 billion to build on Earth. It employs thousands of highly trained engineers and technicians across dozens of specialties. The supply chain feeding that fab includes silicon wafer manufacturers, photoresist chemical producers, specialty gas suppliers, precision optical component makers, ultra-pure water treatment system providers, rare earth element refiners, and dozens of other specialized companies spanning multiple continents. A self-sustaining city on Mars would eventually need to manufacture its own semiconductors, not immediately. The first decade might rely on stockpiled chips brought from Earth. But semiconductors degrade over time, equipment fails. Environmental conditions on Mars, including radiation, which can damage microelectronic circuits, may accelerate degradation. Software updates require hardware that eventually needs replacing. Control systems for life support, power generation, water recycling, atmospheric processing, communications, navigation, medical equipment, and industrial machinery all depend on functioning electronics. If the city is truly self-sustaining, it must eventually produce its own electronic components from raw Martian materials. This requires not just a chip fab, but the entire supporting infrastructure: silicon mining and refining, chemical synthesis for photoresists and etching agents, precision glass and optics manufacturing for lithographic equipment, ultra-pure material processing, and a workforce trained in each of these specialized disciplines. This is one product category among thousands. A functioning city requires steel production from raw ore, involving blast furnaces or electric arc furnaces, alloying elements, and metallurgical expertise. It requires glass manufacturing, demanding high-purity silica processing, melting furnaces operating above 1,500 degrees Celsius, and forming equipment. It requires pharmaceutical production using chemical synthesis or biological manufacturing in sterile, regulated facilities with quality assurance capabilities. It requires textile production, meaning either synthetic fiber manufacturing from petrochemical or bio-based feedstocks, or plant-based fiber cultivation and processing with spinning, weaving, and finishing equipment. It requires rubber and polymer manufacturing for every seal, gasket, hose, tire, belt, and insulation material in the settlement. It requires bearing and fastener production for every mechanical system. It requires wire drawing for electrical conductors. It requires optical manufacturing for lenses, sensors, and communication components. It requires ceramics production for electrical insulators and thermal protection. It requires precision machining for replacement parts across every category of equipment. The list extends into thousands of distinct industrial processes, each requiring specialized equipment, trained personnel, raw material inputs, energy, quality control, and maintenance of the manufacturing equipment itself. Robert Zubrin, the aerospace engineer, author of The Case for Mars, and founder of the Mars Society, has been one of the most prominent and persistent advocates for Mars colonization for more than 3 decades. Even Zubrin acknowledges that Mars will not have the division of labor required to make it fully self-sufficient until its population numbers in the millions. This is not the assessment of a Mars skeptic trying to kill the dream. This is the assessment of one of the dream's most committed champions, a man who has dedicated his career to making Mars colonization happen. 1 million people represents the minimum population needed to sustain the diversity of specialized skills, professional expertise, and overlapping industrial processes that a modern technological civilization requires simply to maintain itself, to say nothing of growing and improving. The population challenge extends well beyond mere headcount. A self-sustaining city requires genetic diversity sufficient to maintain long-term population health across generations. Population genetic studies of isolated human communities suggest that minimum viable populations for avoiding dangerous levels of inbreeding and genetic drift range from several hundred to several thousand individuals, depending on assumptions about mating patterns, reproductive equality, and population management strategies. But genetic viability is a necessary minimum condition, not a sufficient one for civilization. Civilization requires deep specialization. It requires doctors, surgeons, anesthesiologists, nurses, pharmacists, radiologists, psychiatrists, dentists, engineers across a dozen subdisciplines, teachers across every subject, farmers, agricultural scientists, miners, geologists, chemists, electricians, plumbers, welders, machinists, metallurgists, materials scientists, software developers, network administrators, biologists, microbiologists, nutritionists, veterinarians if livestock are involved, architects, structural engineers, heating and cooling specialists, and administrators for governance, resource allocation, dispute resolution, and planning. Each of these roles requires years of formal education and practical training. A city of 10,000 people cannot support this specialization depth with any margin. Earth cities function precisely because they exist within a global network of trade and knowledge exchange. A cardiologist in Boston does not need to know how to smelt copper because someone in Chile does that. A semiconductor engineer in Taipei does not need to grow wheat because farmers in Kansas do that. A teacher in London does not need to manufacture their own textbooks because publishers and paper mills and chemical plants and forestry operations spanning multiple continents handle that supply chain. Every city on Earth is profoundly specialized and profoundly interdependent. No city is self-sufficient. The entire concept of urban civilization since the agricultural revolution has been built on the premise that cities trade with their surrounding agricultural hinterlands and with each other. Specialization creates efficiency. Trade creates wealth. Interdependence creates resilience through redundancy at the system level. A Mars city has no one to trade with. It must contain within its own population and its own borders the complete productive capacity of an entire industrial civilization, duplicating from scratch what Earth assembled through centuries of accumulated innovation, infrastructure, and institutional knowledge. The economic logic of a Mars city presents another obstacle that is rarely discussed honestly. On Earth, cities exist because they are economically productive. They create wealth through manufacturing, services, trade, resource extraction, and knowledge work. The wealth generated by a city pays for its infrastructure, its governance, its maintenance, and its growth. A Mars city produces what of economic value? At present, the answer is effectively nothing that justifies its cost. Mars has no known resources that are economically viable to extract and transport back to Earth. The transportation cost alone makes physical exports absurd. Even at SpaceX's most optimistic projected pricing, shipping physical goods from Mars to Earth would cost thousands of dollars per kilogram. There is no material on Mars, no mineral, no metal, no chemical, that cannot be obtained more cheaply on Earth or from asteroids in easier-to-access orbits. Intellectual property, scientific data, and research insights could theoretically be exported at the speed of light, but a research station producing valuable science is not a city. A city of 100,000 or 1,000,000 people needs an internal economy that sustains its own population with meaningful work, income distribution, and resource allocation. Without trade-based economics, a Mars city would exist as a pure cost center, sustained entirely by financial subsidy from Earth governments, private investors, or some combination thereof, for decades and potentially centuries before it could hope to develop any basis for economic self-sufficiency. The historical precedent is not encouraging. European colonies in the Americas, which had breathable air, drinkable water, farmable soil, exploitable resources including timber, furs, fish, tobacco, sugar, and mineral wealth, indigenous labor that could be coerced into the colonial economy, and ocean-based trade routes connecting them to wealthy home markets hungry for raw materials, still required decades to centuries of subsidized investment before achieving economic viability. The Virginia Company, which funded the Jamestown settlement in 1607, went bankrupt within 17 years despite the colony eventually developing a profitable tobacco crop. The Massachusetts Bay Company required continuous investment from wealthy Puritan backers for decades before the colony became self-financing. Many colonial ventures failed entirely, their investors losing everything and their settlers dying of starvation, disease, and conflict. Mars offers none of the natural resource advantages, none of the agricultural potential, and none of the trade relationships that sustained even the most precarious and marginal colonial enterprises in human history. Some advocates have proposed intellectual property as an export that could sustain a Mars economy. The idea is that the unique challenges of Mars living would drive innovations licensable back to Earth. This is theoretically plausible but quantitatively insufficient to support a city-scale population. The entire global intellectual property licensing market generates roughly $300 billion annually. A Mars settlement struggling to keep its inhabitants alive would need to somehow become one of the most productive innovation hubs in the solar system, competing against every university, laboratory, and technology company on Earth, all of which operate at a fraction of the cost in environments vastly more conducive to research. The notion that desperation and constraint automatically produce superior innovation is a romantic narrative that rarely survives contact with the reality of resource-starved frontier communities. Repair and maintenance represent an invisible but relentless challenge that silently undermines every plan for self-sufficiency. Every machine breaks, every seal wears out. Every electronic component eventually fails, every bearing degrades, every filter clogs, every pump loses efficiency. On Earth, the global maintenance and repair industry is enormous, employing millions of people and consuming vast quantities of replacement parts flowing through supply chains that span continents. When a pump fails in a factory in Ohio, a replacement is ordered from a distributor who stocks inventory from a manufacturer who sources components from suppliers across multiple countries. The replacement arrives in days, sometimes hours. On Mars, a failed pump must be repaired with locally manufactured replacement parts, or cannibalized from another system which then loses that capability, or the function it served goes unperformed until the next supply ship arrives from Earth, potentially more than 2 years later. If the failed pump is part of the water recycling system, or the atmosphere processing system, or the thermal regulation system, the gap between failure and repair is not an inconvenience. It is a survival crisis that escalates with every hour. The concept of maintenance cascades is critical to understanding why self-sufficiency is so difficult. A single critical failure can trigger a chain of secondary failures. If the power system degrades, the atmosphere processor runs at reduced capacity, which affects air quality, which affects human health and cognitive performance, which affects the ability of the maintenance crew to diagnose and repair the original power system problem. On Earth, this cascade is interrupted by the ability to call for external help, order replacement parts overnight, or evacuate affected personnel to safety. On Mars, none of these interruptions are available. Every cascade must be resolved internally, using only local resources and expertise. The concept of technological regression further complicates the self-sufficiency equation. Even on Earth, isolated communities that lose access to external supply chains experience rapid technological decline. When the Roman Empire collapsed, regions that had relied on Roman supply networks for tools, metals, glass, and processed goods reverted to more primitive technological levels within generations. The knowledge and skills needed to maintain Roman-era technology were lost because they depended on supply chains and specialization networks that no single community could replicate internally. A Mars settlement that loses reliable supply from Earth would face an analogous risk of technological regression, potentially sliding from a high-technology habitat-based civilization towards something far more precarious as equipment fails faster than it can be locally manufactured. Now multiply this scenario across every system in the settlement, from life support to power generation to agriculture to medical equipment to transportation. The maintenance burden of a city-scale installation on Mars is staggering, and every single dependency on Earth for parts, materials, or expertise is a thread of vulnerability that contradicts the claim of self-sufficiency. Governance and social organization complete the picture of requirements that lie entirely outside SpaceX's domain of expertise and competence. A city is not a collection of buildings and machines operated by a workforce. It is a social organism composed of humans who disagree, compete, cooperate, form alliances, break alliances, fall in love, raise children, grieve losses, experience mental illness, struggle with addiction, hold grudges, create art, seek meaning, and require frameworks for resolving the inevitable conflicts that arise whenever human beings share finite resources in stressful environments. Who governs a Mars city? Under whose legal authority does it operate? SpaceX is a private corporation incorporated in the state of Delaware under United States law. Does Delaware corporate law apply on Mars? Does United States federal law? The Outer Space Treaty of 1967, to which every major spacefaring nation is a signatory, prohibits national appropriation of celestial bodies and requires that the exploration and use of outer space be carried out for the benefit of all countries. If no nation can claim sovereignty over Martian territory, what legal framework protects the rights of people living there? What prevents the entity that controls life support from exercising absolute authority over residents who cannot leave? What labour protections exist for workers who cannot quit and relocate to a competitor? What happens when the second generation of Mars-born residents, who never chose to live there, disagrees with the governance structures established by the founding generation? These are not theoretical philosophy seminar questions to be deferred to future generations. They are practical, immediate, operational requirements for any community larger than a small research team operating under a clear military-style chain of command. History demonstrates that every human community beyond approximately 150 people, the so-called Dunbar number for maintaining informal social relationships, requires formal governance institutions to function. A city of thousands or tens of thousands of people living in the most stressful environment humans have ever inhabited, with no possibility of physical exit from the community, requires governance structures of extraordinary sophistication and legitimacy. Designing those structures is a task as complex and uncertain as any engineering challenge on the list, and it has received virtually no serious attention in SpaceX's public communications about Mars settlement. The February 2026 pivot to the Moon illuminates all of these realities with uncomfortable clarity. When Musk announced that SpaceX would prioritize building a self-growing city on the Moon before pursuing Mars settlement, he explained the rationale in terms of iteration speed. The Moon allows launches every 10 days with a 2-day trip time. Mars allows launches every 26 months with a 6-month trip time. This means problems discovered during lunar operations can be addressed, redesigned and tested again within weeks. The same problem on Mars delays the next iteration by more than 2 years. If the most capable launch company in human history recognizes that building a settlement, even on the nearby, relatively accessible Moon, requires years of rapid iteration to get right, the implication for Mars, which is orders of magnitude more distant, more hostile, more isolated, and more demanding, is deeply sobering. Musk said SpaceX would begin Mars city efforts in 5 to 7 years, but he also said that achieving a self-sustaining city on Mars would take 20 or more years from that starting point. That timeline pushes the actual achievement of a Mars city to the 2050s at the earliest, assuming no further delays, no unexpected technical barriers, no funding disruptions, and no additional pivots in strategic priority. The history of SpaceX's Mars timelines includes predictions of an uncrewed Mars mission by 2018, a crewed mission by 2024, and uncrewed cargo missions by 2026, none of which materialized. This is not evidence of dishonesty. It is evidence that Mars imposes constraints that even the most capable and motivated engineering organization in the world cannot will away through ambition and iteration speed. What does all of this mean for the original question? It means that SpaceX may absolutely land humans on Mars. The company's track record in rocketry is extraordinary and continues to advance rapidly. Starship represents a genuinely revolutionary launch vehicle that, once mature, will be capable of delivering unprecedented quantities of mass to the Martian surface. SpaceX may help establish an outpost, a research station, perhaps eventually a small permanent base maintained through regular supply missions during transfer windows. These achievements would be historically significant. They would expand the boundaries of human presence in the solar system. They would produce scientific knowledge of enormous value. They would inspire generations. But a self-sustaining city on Mars, a true city, requires solving problems that are not in SpaceX's domain and may not be in any single organization's or generation's domain. It requires biological knowledge we do not possess about human health in low gravity across lifetimes. It requires radiation mitigation technologies that exist only in concept. It requires closed-loop life support systems operating at reliability levels never achieved in any comparable system on Earth. It requires industrial manufacturing capacity that presupposes a population and infrastructure base that cannot exist without the industrial capacity coming first. A bootstrapping paradox that has no obvious solution at any scale smaller than millions of people. It requires an economic foundation that currently has no identified basis. It requires governance and legal frameworks designed for circumstances unprecedented in human history. And it requires every one of these things simultaneously, operating without critical failure on a planet where the consequence of any sustained failure in any major system is death. The dream of a city on Mars is not a lie. It is a vision. Visions matter because they organize resources and attention around goals that produce real-world benefits along the way. Starship, regardless of its ultimate destination, is already transforming space access in ways that benefit satellite deployment, space station construction, lunar exploration, and scientific observation. The technologies being developed for Mars life support will improve sustainability on Earth. Materials science, robotics, autonomy, and closed-loop resource management research driven by Mars ambitions will find applications across terrestrial industries. The dream is productive even if its ultimate endpoint remains far beyond our current reach. But intellectual honesty requires distinguishing clearly between what is plausible in the near term and what remains speculative across generational timescales. SpaceX may help humanity reach Mars within the next decade. SpaceX may help establish the first permanent human presence beyond Earth and the Moon. These are monumental world historical contributions that deserve celebration, investment, and support. A true city on Mars, a self-sustaining settlement of hundreds of thousands or millions of people capable of surviving independently of Earth across multiple generations, is a challenge of a fundamentally different kind. It is not a transportation problem with a rocket-shaped solution. It is a civilization problem. And civilizations are not built by rockets, any more than civilizations on Earth were built by sailing ships. Ships brought people and cargo to new continents. Civilizations were built by the slow, difficult, costly, iterative accumulation of agriculture, industry, knowledge, institutions, culture, governance, medicine, and social organization across decades and centuries of sustained effort by millions of people. As the Jamestown example showed earlier, even colonial ventures on a habitable planet with breathable air, drinkable water, farmable soil, timber, game, and navigable rivers required centuries of subsidized investment and millions of immigrants before achieving industrial self-sufficiency. The Mayflower crossed the Atlantic in 1620. The United States did not become an industrially self-sufficient nation until the mid-1800s, more than 2 centuries later. The timeline for true Martian self-sufficiency, if it is achievable at all, should be measured not in the decades that SpaceX presentations suggest, but in the centuries that the historical record of civilization building demands. A Mars settlement would need to achieve a comparable level of industrial independence while starting from a far smaller population base in a far more hostile environment with far less accessible natural resources and with no possibility of receiving the continuous waves of immigrants, manufactured goods, and accumulated knowledge that sustained every successful colonial development in human history. Mars may host crewed missions in the 2030s. It may host a permanent research base by mid-century. It may host expanding infrastructure and a growing human presence through the latter decades of this century. These are achievable goals that the current generation of engineers, scientists, and policymakers can meaningfully work toward. But anything that deserves to be called a true city, a place where people are born, live full lives, raise families, grow old, and pass their world to the next generation without ever depending on a supply ship from Earth likely lies beyond the horizon of anyone alive today. Not because the dream is foolish, not because Mars is impossible, not because SpaceX has failed, but because building a civilization is the hardest thing humans have ever done, and we have only ever done it once, on a planet that spent 4 billion years preparing itself to support us. SpaceX is building the road to Mars. That matters enormously. Roads make everything that follows possible. Without the road, there is no outpost, no base, no research station, and certainly no city. SpaceX's contribution to humanity's future on Mars may prove to be the most important single contribution any organization makes. But the road is not the destination. The destination requires everything the road cannot carry. It requires answers to biological questions we have not yet asked. It requires industrial capabilities we have not yet imagined at Martian scale. It requires social structures we have not yet designed. It requires economic models we have not yet invented. It requires time, measured not in starship flight schedules but in the patient, generational arc of civilization itself. The destination is immeasurably further away than the road alone can carry us. And the first step toward reaching it honestly is admitting how far we still have to go,